A has been such a mess.
That's an awesome day now.
Yeah, Justin. Shh. What do you got? 8 and 10. Let's do 8, because I think 8 is a little more... Okay, so here we go. Let's do number 8. So what do we got? 5.4, number 8. Okay, so here's our figure. Shh. Let's quiet down, you guys. I know that croissants are delicious. All right, so there we go. So here's our drawing. So the problem tells us that the force of gravity on block A is 102 newtons, and that the force of gravity on block B is 32 newtons. It says the coefficients of friction between A and the incline are, and then there's these ridiculous numbers. 0.56 is static, and 0.25 is kinetic. The angle is 40 degrees. Man. Let the positive direction of an x-axis be up the incline. We usually would not call that an x-axis. What would we call that? Parallel axis, right? So it's just saying up the hill is positive. In unit vector notation, what's the acceleration of A if A is initially A at rest, B moving up the incline, C moving down the incline? All right, so I guess we should probably figure out the forces on our system here. So let's see. So the force of gravity on B is 32 newtons, right? Over here, I care about my FG parallel on A, which is going to be 102 times the sine of 40. 102 sine 40. So that gives you 65.56. Good. There's also a perpendicular component, which is the same thing but with cosine. So that gives you 78.14. So now I know my normal force. Is everybody cool with why the normal force is equal to the perpendicular one in this one, but it wasn't in the last example? All right, what's my next step? Find friction, right? So over to the side, let's find our force of friction static max. So that's going to be our normal force times 0.56, which is 43.76. And we might as well find our kinetic while we're at it. Croissant. 19.53. Okay, good? Yes. All right, so question A wants to know what the block will do if it's initially placed at rest. So what are the choices? Either it can accelerate down the ramp, accelerate up the ramp, or stay at rest, right? Thoughts about where we go? What should our first question be? Does it move? And if it doesn't move, why would it not move? What would be preventing it from moving? Static friction, right? So our question at this point ought to be, can static friction prevent the motion? You're nodding, Seba. How come?
Because
guys, back to
you pull a 32 and then you have whatever it is, 43 going that way. Even without it, the parallel force is going to keep it from going up.
Oh, I gotcha. So you're saying that the static friction is going to go down the hill to prevent it from going up the hill?
No. I mean, right now it's going to go down.
Yeah, right now it's going to go that way, and the static friction is going to go that way. So why is 43 enough? 43 is not as big as 65.
65 minus 13.
There you go. So what you want to do is you want to kind of ask yourself, how much force would friction need to make the net force 0? Follow? Okay. So right now, I've got 65 pulling sort of down the ramp and 32 pulling up the ramp. So I need another, what, 33 newtons? Follow? Okay. So for question A, you're going to have a force of friction static, that's an F, that's big enough to make your net force 0. So in other words, 32 minus 65 plus something equals 0. Follow?
Yes.
Justin, you good? Everybody good? Question, Johnny? Or you just good? Okay. Oh, sorry, Johnny. All right. Okay, so that's A. B says, what happens if the box is already moving up the incline? So if it's already moving up the incline, then how do I finish my drawing? It's already moving up the incline. You're pointing down, Evan. How come? Because you'd have to have kinetic friction going down the incline, right? And my kinetic friction is 19.5. Follow? So then we can use our net force and find our acceleration, right?
Yep.
Is that good? Do I need to finish, or are we good up to there? Oh, really? Well, let's figure out what it gets. So for part B, let's see. So your net force then is going to be 32 minus 65.56 minus our kinetic friction of 19.53, right? So what's that give you? Sorry?
Maybe I switched up the sign.
Well, let's see. 65.56 minus 19.53. So you get negative 53.1 newtons.
I think I misread like where it was going.
Okay.
I thought that it was just enough time because the 33 newtons would get to like pull it, that it would just start falling down.
I gotcha. Right. So yeah, and so this is something that I'm really focusing on with my honors students right now. So remember, you guys, friction resists motion. It opposes motion, not force. So even though there's technically more force down the hill, it doesn't matter. What matters is the direction it's moving. If it's moving up the hill, then no matter what, friction's going against that motion.
And vice versa.
And vice versa. Sorry?
Knowing that.
Okay. All right. Are we good, you guys?
Yes.
All right. And then in C, it says, what if it's moving down the ramp? So then, which way is our friction going to go now? Up. And so then you just make your kinetic friction positive, right?
I think it asks for unit vector notation.
Oh, did it? Oh, that's right. Oh, it asked for unit vector notation. Gotcha. Well, what's your y? So they use, what's your perpendicular acceleration going to be? 0, right? Okay. So all of our acceleration is going to be along the air quotes x-axis, right? Because they defined the x-axis to be this way, right?
So when you're doing vector notation, you don't have to do it according to the actual x-axis.
You're using the x-axis that the problem defines.
So you would have to break up into...
Correct. Yeah. So your acceleration is just whatever your acceleration is.
Yes. Yeah, that was what I was wondering.
Gotcha. Does that make sense? Thank you for saying that. Do you guys see what I'm saying?
Yeah.
Yeah, Seba?
So when you find the acceleration, do you find you're dividing by the mass of A?
No, it's the whole system here.
Okay.
Good question. Yeah. So to find the acceleration, where all of this net force that I just found is the net force for the whole system, right? And therefore,
Why isn't it the net force of just A?
because just A wouldn't have this force of gravity acting on it. It would have tension force acting on it. And that tension force would be some number less than 32. Genuine okay, or?
Not really.
Okay, so, all right, so let's finish it. Let's finish B. Okay. All right, so for B, here's our net force, right? So this is the force of gravity on object B. This is the parallel component of gravity on object A. And this is the force of kinetic friction on object A, right? So I've got forces on A and forces on B here. So this is the net force on objects A and B. Okay? Why then am I not worried about tension here, you guys? This is an important question. Why do I not need to worry about the tension?
Oh, it's an internal force.
The string is taut because it's pulling object A up the ramp.
What's an internal force?
There you go. It's an internal force.
So when would you need to worry about friction?
When would I need to worry about friction?
If you're-
I did worry about friction. I said we didn't worry about tension.
I'm sorry, I meant tension.
Okay, let me come back to that in a second. Okay, so for right now, because we're dealing with A and B in the spring as our system, the tension is an internal force. Everybody good with that? All right, so to find the acceleration of the system, it's net force over mass. So the net force is negative 53.1 newtons. The mass is...
Talking about acceleration.
Did anybody find the mass by any chance?
13 point something, I think.
Yeah, so it's 102 plus 32 divided by 9.8, 13.67. So divide that out, and you get an acceleration of negative 3.88 I meters per second squared, right? And the I just means along our negative x-axis. All right, are we all good up to this? All right, so to Sebo and Margaret's question. We could, and it's worth, this is a thing you should absolutely be able to do. We should be able to find the tension in the rope now.
Yeah.
So your question was, when would you need to worry about it? You have to worry about the tension if you're looking at a system for which the tension is an external force. Okay? So in order for the tension to be an external force, we need to pick a system that doesn't include the rope. So
like just the block.
So just either of the two blocks. Follow? So let's do that real quick since we've got some questions about it. All right? So view dual page on. Okay, so let's look at block A. This is the harder choice, but we can do it anyway. So what forces act on block A? Well, there's FG parallel, which is 65.56 newtons, right? It's going up the ramp, so friction's going down the ramp. So we've got a kinetic friction force of negative 19.53 newtons. And then we've got some amount of tension pulling it up the ramp. Tell me what you just realized, Margaret.
The tension.
Okay.
Of that block.
Right, because so the tension is provided by this other block, creates tension in the rope and pulls A up. Now, that doesn't necessarily mean it's moving up the ramp. Oh, well, I guess it is in this one. But all right, so are we good?
Yeah, and also too, wouldn't it be if you're just focusing on the block?
Yeah.
Sorry.
Oh, when you say the block, you mean the other one?
No, the A. If you're only-
Either block individually, yes. All right, are we good? All right, so now how do we find the tension?
Net force.
Net force equals net force, right? And we know our acceleration is negative 3.88, right? So now we just go net force equals net force. So the mass of this guy was whatever 102 divided by 9.8 is. 102 divided by 9.8 gives you 10.4. So you get 10.4 times negative 3.88 equals tension minus 65.56 minus 19.53, and solve for your tension. Okay, so let's do it real quick. So let's see, so times negative 3.88 plus 65.56 plus 19.53, and it gives you your tension force ends up being, oh, what did I do? Which way is the system accelerating? The system's going up the ramp. Wait a minute. Oh, right, it's slowing down. Thank you. Yeah, okay, so we're good. So your tension ends up being 44.7 newtons. So the idea is it's moving up the ramp, but slowing down. So your two downward forces have to be winning, right?
Yeah.
Follow? All right. And then from the perspective of the other block, the force of gravity on this is 32 newtons. If it's moving down and you want to slow it down, then you need more upwards force, right?